Cloud developers often select regions and zones from a drop-down menu, treating them as simple software configurations. Treating these physical layers as mere abstractions leads to catastrophic architectural flaws. A single misconfiguration in how you distribute your nodes dictates whether your application survives a physical fiber link cut or goes completely dark during a local power grid failure. Today, we are bypassing the basic definitions to look directly under the hood at how regions and zones are physically engineered. We will analyze the mechanics of cluster-level isolation and explore the specific trade-offs inherent in region selection. Mastering these physical fault domains provides the decision matrix required to engineer systems capable of surviving localized hardware deaths and massive regional disasters. This geographic map models the baseline architectural scenario: a single application deployed in a single corporate data center in London, actively receiving a data packet from a user in Mumbai. From an engineering standpoint, this architecture suffers from two immediate bottlenecks. The first is severe user latency. Because of the sheer physical distance those packets must travel across the globe, that user in Mumbai experiences slow load times. The second bottleneck is a massive availability risk. If that specific physical building in London suffers a hardware collapse or loses power, your entire application goes down instantly. To solve the single building risk, we evolve the architecture by adding a second data center within the same London metropolitan area. If London Data Center A suffers a major outage, traffic immediately routes to London Data Center B, keeping the application online. However, a citywide power grid failure or an extreme weather event will take both of those local data centers offline simultaneously. This vulnerability requires a final evolutionary tier, deploying across multiple geographically separated regions, such as London and Mumbai. Multi-region deployment fully isolates the regional failure domain. If the entire city of London goes dark, a global load balancer instantly routes all incoming traffic to Mumbai. This also solves our original latency challenge by placing application instances physically closer to those global users. Geographic distribution serves as a fundamental engineering requirement for mitigating the physical constraints of distance and systemic local threats. This global map displays a massive physical footprint of over 20 distributed region nodes. A cloud region represents a sprawling physical collection of grouped resources across a wide geographic area. Selecting a region requires balancing four rigid engineering and operational trade-offs, as shown in this comparison matrix. The first constraint is compliance and data residency. Certain countries enforce strict legal regulations requiring that citizens' private data remain physically within national borders, which dictates exactly where you can legally deploy. The second constraint is user latency. The physical fiber path length between your servers and your users dictates round-trip speeds, requiring proximity to your primary user base. The third constraint is service availability. Cloud providers pilot new infrastructure in specific target regions first, so the catalog of managed services varies globally. The fourth constraint is pricing dynamics. The cost of a virtual machine or storage resource varies based on geography. Cloud providers price resources based on local land costs, power rates, and taxes, creating significant regional variation. Selecting a region requires a precise calculation of legal jurisdictions, physical laws of latency, service catalogs, and regional economics. Zones provide high availability without the severe latency penalty of crossing oceans. An availability zone is an isolated physical location situated within a parent region, and every region contains at least 3 of them. A look inside one zone reveals multiple separate data centers, each housing independent physical cluster racks. Each cluster operates as an independent physical infrastructure unit, complete with its own isolated servers, network switches, and racking. To ensure isolation, these zones run on entirely independent utility power grids. They also utilize isolated physical cooling infrastructure and maintain separate network carrier connections. This engineering ensures containment. A catastrophic fire or power grid collapse in Zone A physically cannot cascade to Zone B or Zone C. Despite this physical isolation, zones within the same region are linked by ultra-high-speed, ultra-low latency fiber. These low-latency links enable synchronous data replication and active-active application clusters. Zones allow your architecture to survive the death of an entire data center in real time, all within a single geographic market. This logic flowchart serves as a practical system design matrix, linking specific availability targets directly to the correct infrastructure layer. Surviving a local data center failure requires distributing your compute instances across a multi-zone architecture within a single region. Surviving an earthquake or a citywide outage requires scaling up to a multi-region distribution. Complying with national data residency laws requires selecting a precise, legally compliant regional location. Deploying in a single zone is insufficient for high availability. A single zone failure will bring your application down if your workload isn't spread across multiple domains. Pricing is not uniform across regions. Zone counts vary. Zones often hold multiple buildings. Multi-region architectures are accessible to startups. This naming convention manifests globally. In North America, US-1-1 contains zones A, B, and C. The same taxonomy applies to Europe-North 1 in Finland and Asia-South 1 in Mumbai. Designing resilient, cloud-native systems requires mapping your software architecture directly to these unyielding physical boundaries.